So dissolving a solute into a solvent is an equilibrium process, similar to evaporation. Evaporation was an equilibrium process. So what we see initially is the rate of dissolving is much higher than the rate of recrystallizing, because you can't have any compound recrystallizing if there aren't any ions dissolved in the first place. But as the concentration of dissolved solute increases, then the rate of recrystallization increases. And at some point, those two rates will become equal to each other, and we get a dynamic equilibrium. So if we have a solution of salt that is concentrated enough that it has some salt sitting in the bottom still, it's actually not the same salt all the time, because that salt is continuously dissolving and recrystallizing. And you can actually see that the crystals are changing in shape over time. Here we're looking at some sodium chloride being added to water. There are no sodium or chloride ions in the water yet, so there's no recrystallization. So the ions start to dissolve. They get solvated. Remember, the water molecules come around them, and they've got the ion dipole forces, and they lure them away from the sodium chloride. Once we have some ions in the solution, well, I guess we should look at this down here. So right now, dissolution is greater, that rate is greater. More is dissolving than is recrystallizing. But when we get enough sodium and chloride ions dissolved in the water, then the recrystallization is going to get larger as that concentration increases. And at some point, these will be equal. So this is like the evaporation of molecules and then the condensation. So if these ions that are, have their little water groupies around them, if they bump into this salt crystal, they might stick and become part of the crystal again. So a saturated solution is one in which the dissolved solute is in dynamic equilibrium with the solid solute. So that's what I was describing as a sodium chloride solution where you've dissolved sodium chloride. It can take a lot, but you've added so much that you got to the point where there's some still sitting on the bottom and no more will dissolve. That is a saturated solution. So like a saturated sponge, it's full, right? It's full of that solute. If you add more solute, it's not going to dissolve. An unsaturated solution has less than the equilibrium amount of solute. So if you add more solute, it will dissolve. Unsaturated. And then we have the seemingly impossible, the supersaturated solution. Supersaturated solution has more than the equilibrium amount of solute that's actually dissolved. It's not that it's sitting on the bottom. Often students confuse supersaturated and saturated. The saturated solution is where you have the solution and you've got some of the solute just sitting on the bottom. Here, all of this solute is dissolved, but you've got more dissolved than is possible. How does that work? Well, solubility is temperature dependent.
Is it a trick in the matrix?
Pardon me?
Is it a trick in the matrix?
A trick in the Matrix. One of these days I really have to see that movie. I've never seen the Matrix. I know, right?
How to get your life together. After this class is done, that's
I'll put that on my list of things to do.
As soon as the class is
So
over.
this is a picture of a beaker containing supersaturated sodium acetate. Yeah, sodium acetate. Oh yeah, it's written right here. And the way the supersaturated solution was created is at an elevated temperature, you can get more solute to dissolve because the solubility is higher. And so you dissolve it at a higher temperature, and then you let it cool down very slowly. And you don't bump it, and you don't put things into it. You try not to look at it or even think about it. Once it is disturbed here by touching with a glass stirring rod, it's like poking the solution and saying, hey, you can't do that. That's not possible. And it goes, oh, you're right. And then all the excess solute crystallizes out. So this reminds me of Bugs Bunny and Roadrunner, right? So the Roadrunner cartoons, the Roadrunner was always, well, lots of people were always running off of cliffs out in the desert, right? And they didn't just like fall over when they took that first step. They run in the air, right? Until they realize they're not on the ground anymore, and then they fall, right? It can't happen in real life. But this is like the Roadrunner or Wile E. Coyote that's run off the cliff and they're on air. And then you poke them and say, hey, you're not on the ground anymore, and then they fall. Okay, so here are a couple of videos. So that's a supersaturated solution. So I'm just sticking a rod in there. So those are crystals of sodium acetate. Nice. Okay, thank you. And they're growing. Makes a lot of crystals. There was way too much dissolved in there. It is cool, but it's also warm.
In a series of experiments.
No, we do not want to hear that again. Okay. Let's look at this one. This one doesn't have sound either. But this is where they've made sodium acetate solutions, and then they're having fun with them. So they're sticking some toothpicks in there and making little pom-poms grow. And there's the temperature, 52 degrees. So it was probably around 20, 25 degrees before the recrystallization happened.
That's pretty cool.
It's
That's instant.
It's pretty warm cool. Yeah. So sometimes it's referred to as hot ice because it looks like it's freezing, doesn't it? But it's actually warm.
Why can we do a lab like that? That lab looks cool.
I know, right? Building sandcastles. Part of the trouble is it takes a long time because you have to make the solution at a high temperature and wait for it to cool off, which is really boring.
Oh, is the cooling aspect of it takes forever? Is that
Yeah. And you can't hurry it up or it realizes that it walked off the cliff.
So I'm assuming it would be like an overnight thing type of?
Depending on the size of the flask, I mean, you can do it in like an hour or two, but
Interesting. So curious, is this something similar to what happens to like ice skating? Is that something similar to it or no?
no.
I feel like I've seen something like that, like in the rings or Alaska or something like that. So I was wondering if it's the same mechanism or same type of.
Are you struggling in your calculus class?
No, I'm not. Not struggling in my calculus class. Thanks for asking.
I wondered if it's the same mechanism or same science underneath it or something.
I think you can get super cooled water that's, it's below the freezing point. It just hasn't frozen yet. And then if you disturb it, you could see something like this happening where it's actually freezing. Yeah. So supersaturated solutions are unstable. They are not going to stay that way. Here we've got a graph showing the solubility, which is the grams of solute that will dissolve in 100 grams of water as a function of temperature. And so we see that for most solids, as you increase the temperature, the solubility goes up. Some of them quite dramatically. Potassium nitrate is way up. So at, just above 55 degrees or so, you can actually dissolve an equal amount of potassium nitrate in water. So if you had 100 grams of potassium nitrate and 100 grams of water, you could make a solution out of it, which is kind of crazy when you think about it. Here's our friend table salt, sodium chloride. It is slightly more soluble at higher temperatures, but it doesn't change very much, which is probably good for the fish in the ocean. And then there's some weird compounds. Cerium sulfate is one of them. They actually become less soluble when you heat them up. Kind of weird. So recrystallization is what happens when those ions that were in solution come and become parts of the crystal again. And this can be used as a technique to purify a solid. So you prepare a saturated solution at an elevated temperature and you let it cool slowly. Now, most solutes will not form supersaturated solutions. So this is not going to become supersaturated, but it's going to form crystals slowly, not crazy fast like the ones we saw in the video. And those were not sped up or anything, that was real time. As the crystal forms, the crystalline structure tends to reject impurities because those ions want to fit together in a particular way. And so if something else comes in there, that's likely to dissolve again and allow the correct ion to come in there. So you can reject impurities and you can make really nice big crystals here. So this is rock candy, which is just crystallized sugar. So you can make some pretty big chunks of solid sugar there. If you want to make rock candy at home, I recommend finding some instructions, because I remember trying that as a child and I didn't realize the elevated temperature part, and that it has to be saturated at an elevated temperature. And so I wasted a lot of sugar and ended up with just sweet string, right, that was wet. So that's something you can do at home, but get some instructions. So those, we talked about solids in water. Let's talk about gases in water. So the effective temperature on the solubility of gases is the opposite of that for solids. Generally, the solubility of gases gets lower with increasing temperature. So we observe that warm soda goes flat faster than cold soda. Here they've got bottles of soda. This one is refrigerated, this one's nice and cold, this one is warm. When you pour the warm one, you're going to get a lot of fizzing because that carbon dioxide is coming out of solution. Whereas with the cold one, you'll get a lot less fizzing. So, tip for making root beer floats. It's a good idea to chill the root beer. Otherwise, as you add the ice cream, it just foams up. We also observe that oxygen levels are lower in warm lakes and rivers. And this is one of the reasons why, if you're keeping fish in an aquarium, there are some fish like goldfish that are good with cooler temperatures, but tropical fish need warmer temperatures. And it's not just because they need to be warm, but they're designed to have higher oxygen levels in the water. I'm sorry. They are okay with lower oxygen levels in the water at the warm end. So you can get thermal pollution of lakes and rivers. Say a factory is dumping wastewater into the river. That water may be perfectly good water, really nice and filtered, but if it's hot, then it's going to raise the temperature of the river, which is going to decrease the oxygen content and cause fish and other things to die that depend on the oxygen. And of course, global warming then becomes an issue with that as well. Pressure has an effect on the solubility of a gas. So if the pressure of the gas above the liquid is high, then more of the gas is soluble. So the example here is a soda can pressurized with CO2. When you open the can, we've released the pressure, and now the solubility of CO2 in there goes down, and the soda begins going flat. Now, I actually did not plan this, but I have a bottle of fizzy drink here. Let's open it and see what happens.
You should have shook it first.
No. Well, we heard the noise. This is not super carbonated. Sometimes you can actually see when you release the pressure, you see little bubbles coming up. It could be that this is just not clear enough to be able to see that. Any questions? So here we have one of those piston assembly things where we have CO2 in equilibrium with, this is basically soda water down here. If we push down on this plunger, making this headspace here smaller, that's going to increase the concentration of CO2 and is going to cause more of it to dissolve in the water. So there'll be more dissolved. If we pull up on the plunger, that lowers the pressure and will cause less to be dissolved. So this is why, 2-liter bottle of soda, you want to keep the lid on it when you're not pouring, right? Because you'll build up a certain pressure, the vapor pressure of CO2 in there, and that will keep more CO2 from coming out. If you have this open to the air, the CO2 is just going to keep coming out until it gets to the solubility level at whatever temperature it is, and that's not going to taste fizzy. We can quantify the relationship between gas solubility and the partial pressure of the gas. So that's called Henry's law. The solubility of the gas, which is usually measured in moles per liter, is equal to a constant times the partial pressure of that gas. So this is called the Henry's law constant. That's going to depend on the gas and on the solvent and on the temperature. So it's like, well, how constant is that really? But here are some Henry's law constants for some gases. These are all for these gases dissolved in water at room temperature. So the higher the pressure, the higher the solubility of the gas. So determine the solubility of oxygen in water at 25 degrees Celsius exposed to air at 1 atmosphere. Assume a partial pressure for oxygen of 0.21 atmospheres. So we need the Henry's law constant for oxygen, 1.3 times 10 to the negative third, and that's molarity per atmosphere. 1.3 times 10 to the minus third. Let's write that down before I forget it. 1.3 times 10 to the minus third, molarity divided by atmospheres. I know, it's a weird unit. So the solubility of oxygen is going to equal the Henry's law constant times the partial pressure of oxygen. It's not the total pressure, it's the partial pressure of the oxygen. And that is told to us here, it's 0.21 atmospheres. So we're going to take the Henry's law constant, 1.3 times 10 to the minus 3, molarity per atmosphere, and we're going to multiply by 0.21 atmospheres. get an answer. Of 2.73 times 10 to the minus fourth molar. And that would have 2 sig figs. So you can calculate the concentration of oxygen in water if you know the partial pressure of the oxygen above the water and the temperature.